Welcome to the fascinating science of the salting order paradox, where timing changes everything in cooking. When you salt meat, something remarkable happens at the molecular level, but the timing determines whether you get tender, juicy meat or something dried out. Let's start by understanding the basic process of what happens when salt meets meat. When salt contacts meat, the crystals dissolve into sodium and chloride ions in the surface moisture. Sodium chloride dissociates into sodium cations in chloride anions. These ions spread across the meat surface, creating a concentration gradient that drives the entire process. Now here's the key. Two competing processes happen at the same time, and timing determines which wins. The first process is osmosis, which initially draws water out of the meat. The high concentration of salt on the surface creates a powerful osmotic pressure gradient. Osmotic pressure equals the Van Hoff factor times molarity times the gas constant times temperature. Let's work through a real calculation to see just how strong this pressure is. For sodium chloride, I equals 2 because it dissociates into two ions. A saturated salt solution has a molarity of about 6.15 moles per liter. The gas constant R is 0.082 1-liter atmospheres per mole Kelvin. At room temperature, that's 298 Kelvin or 25 degrees Celsius. Plugging these values in, 2 times 6.1, 5 times 0.0821 times 298. This gives us an enormous osmotic pressure of about 300 atmospheres. This massive pressure drives water molecules out of the meat tissue in the first few minutes of salting. During the first 10 to 15 minutes, you'll see significant water loss from the meat surface. But while osmosis pulls water out, salt simultaneously triggers a second crucial process. The sodium and chloride ions don't just sit there, they actively interact with muscle proteins. Salt denatures myosin and other muscle proteins, changing their three-dimensional structure. Tightly folded proteins unwind and relax when exposed to salt, becoming more open and accessible. Here's the paradox. These denatured proteins can actually hold more water than their original folded forms. But protein denaturation is slower, taking anywhere from 40 minutes to several hours to complete. Now let's map out the critical timeline that determines whether you win or lose with salt. Here's the timeline. 0 to 15 minutes is the danger zone where osmosis dominates. After 40 minutes, you enter the tenderizing zone where protein denaturation takes over. If you cook after just 15 minutes of salting, you get net water loss and tough, dry meat. But if you wait 40 minutes or longer, you get net water gain and beautifully tender, juicy meat. Let's quantify exactly how much water moves in and out during this process. Fick's first law describes diffusion. The flux J equals negative D times the concentration gradient. J represents how many water molecules cross a unit area per unit time. D is the diffusion coefficient, approximately 2 times 10 to the negative 9 meters squared per second for water moving through meat. The total mass transferred equals flux times surface area times time. Let's take a real example, a 200-gram steak with about 50 square centimeters of surface area. In the first 15 minutes, you'll lose roughly 8 to 12 grams of water through osmosis. But after 2 hours, the meat reabsorbs 15 to 20 grams of water through protein denaturation. The net gain is 15 to 20 minus the initial 8 to 12, giving you 5 to 10 grams of extra water retained. That translates to 2 to 5% more moisture in your final cooked product, which is huge for texture and juiciness. But why does this paradox even exist? Why these two opposing processes? Let's ask ourselves, why would nature design a system with such contradictory behavior? The answer lies in the fundamental difference between fast chemical equilibration and slow structural changes. Osmosis is fast, reaching equilibrium in minutes. Protein denaturation is slow, requiring hours for full structural reorganization. The characteristic time for osmosis is much less than the characteristic time for protein denaturation. Temperature dramatically affects both of these processes in different ways. Higher temperatures speed up protein denaturation following the Arrhenius equation. The rate constant K equals A times e to the negative activation energy over RT. In the refrigerator at 4 degrees Celsius, protein denaturation is quite slow. At room temperature, 25 degrees Celsius, the process speeds up significantly. The rate increase going from fridge to room temperature follows this exponential relationship. For typical meat proteins with an activation energy around 50 kilojoules per mole, room temperature denaturation is roughly 3 times faster than refrigerator temperature. Now let's translate all this science into practical cooking techniques. Strategy 1. Salt immediately before cooking, within 5 minutes of hitting the pan. There's no time for significant osmosis to occur, so you get minimal water loss. Strategy 2. Salt 45 minutes to overnight before cooking to get full benefits. This allows complete protein denaturation and maximum tenderness with moisture retention. The danger zone to absolutely avoid: salting 10 to 30 minutes before cooking. Here's your visual guide. Immediate salting is safe. 10 to 30 minutes is the danger zone to avoid, and 45 minutes or longer is best for optimal results. The amount of salt you use also dramatically affects the process dynamics. The typical recommendation is 1 to 1.5% salt by weight of the meat. For a 500-gram piece of meat, that's 5 to 7.5 grams of salt. Higher salt concentration speeds up both osmosis and protein denaturation, but in different proportions. Osmosis rate is roughly proportional to concentration, but denaturation rate increases more slowly, roughly proportional to the square root of concentration. This means that using more salt shifts the balance toward more initial water loss before denaturation catches up. Different types of meat respond differently to salting because of their structure. Let's ask, does this salting paradox apply equally to chicken, pork, and beef? The answer is no. The muscle structure, fat content, and connective tissue all matter greatly. Beef has dense muscle requiring 2 to 4 hours, chicken has loose muscle needing only 1 to 2 hours, and pork sits in between at 1.5 to 3 hours. Fat content also plays a role since fat creates barriers to water diffusion. The effective diffusion coefficient equals the water diffusion coefficient times 1 minus the fat volume fraction. Let's dive deeper into exactly how salt makes meat tender at the molecular level. Salt ions wedge themselves into the actomyosin complex, the tight bond between actin and myosin proteins. The salt breaks actomyosin apart into separate actin and myosin proteins. The tightly bound actomyosin cross-bridges separate, allowing the muscle fibers to relax and hold more water between them. This separation increases the spacing between protein filaments by 10 to 20%. Water holding capacity increases roughly with the square of the fiber spacing. So a 20% increase in spacing translates to about 44% more water holding capacity. Let's work through a complete real-world example with actual numbers. Imagine you have a 300-gram ribeye steak with 60 square centimeters of surface area. You apply 4.5 grams of coarse salt, which is 1.5% of the meat's weight. That works out to 0.075 grams of salt per square centimeter of surface area. At the 15-minute mark, let's calculate what's happened. Osmotic loss is roughly 5% of the total weight, so 15 grams of water lost. Protein denaturation has barely started, maybe 1% effect, only 3 grams regained. Net effect is 3 minus 15, giving you negative 12 grams, a loss of 4% moisture. Now let's see what happens after waiting 2 full hours. The osmotic loss plateaus at the same 15 grams, no additional loss. But protein denaturation is now fully active, creating 12% additional capacity. That's 36 grams. Net effect is 36 minus 15, giving you positive 21 grams, a gain of 7% moisture. That 7% moisture difference is absolutely massive for the final eating quality and juiciness of your steak. Let's address some common mistakes people make with salting. Mistake number 1, salting exactly 20 minutes before cooking, right in the worst part of the danger zone. This timing hits you with maximum water loss, but minimal tenderizing benefit. Mistake number 2, using table salt instead of coarse salt. Fine salt dissolves almost instantly, creating extreme localized concentration that pulls out water too aggressively. Mistake number 3, not patting the meat dry after long salting before cooking. That surface moisture prevents proper browning and crust formation during cooking. Avoid these 3 critical mistakes: 20-minute salting, fine salt, and not drying the surface. Now let's talk about an advanced technique called dry brining that maximizes these effects. Dry brining combines salt application with extended refrigeration time, typically 12 to 48 hours. The optimal protocol uses 1% salt by weight and 24 hours in the refrigerator at 4 degrees Celsius. This gives you 3 benefits: protein denaturation, controlled surface dehydration for better browning, and enzymatic tenderizing. Here's the timeline: initial osmosis for 8 hours, then strong denaturation from 8 to 24 hours, finally reaching equilibrium after 24 hours. The slight surface dehydration actually improves the Maillard reaction, giving you better browning and flavor. Maillard reaction rate is inversely proportional to surface moisture content. Let's bring together everything we've learned about the salting order paradox. Salt creates 2 competing processes: fast osmotic dehydration and slow protein denaturation, each with different timescales. With short salting times under 30 minutes, osmosis wins, and your meat loses moisture and becomes tough. With long salting times over 45 minutes, denaturation wins, and your meat gains moisture and becomes wonderfully tender. The paradox exists because these different molecular mechanisms operate on fundamentally different timescales. Understanding the science behind salting transforms it from folk wisdom into a powerful, controllable cooking technique. The key takeaway: respect the timeline. Either salt immediately before cooking or give it at least 45 minutes. Master this principle and you'll consistently produce tender, juicy, perfectly seasoned meat every single time.